Hi, this is TheoryStation. I'm John Duggan, and this is the Rational Choice Modeling program. The series we're in is Individual and Social Choice. This is the 10th installment in the series. Last time we stated Arrow's theorem and we started setting up the proof. We put some notation into place and I defined the idea of a decisive group. And now we're just going to continue that, and we'll do the proof of Arrow's theorem. So let's, if you remember the setup, we are just taking some social preference function in that intersection of the Venn diagram from last time. So we're assuming that this social preference function we have satisfies rationality, IAA, and Pareto. Now, and what we need to do then is prove that there's someone who's a dictator. So let's just think for a second before we get into this. Consider a group G that's decisive and only has one member. So the number of elements of the group, the number of individuals belonging to the group is 1. So we call that kind of group a singleton, and we can write it like this. It's a set consisting of just one individual, and we can give that person the index I. Now, let's think about this guy. If the group is decisive, what does that mean? Well, since G is decisive, that means that for all alternatives, X and Y, it's decisive for G over Y, which means if the members of that group prefer X to Y, then no matter what anyone else thinks, society also has to prefer X to Y. But here, the group G only consists of this one person, I. So what this means is that for any X and any Y, it doesn't matter what the profile is, if this person prefers X to Y, then society has to also have that preference. But that means this person, I, is a dictator. All right, so the reason I'm pointing this out is because the structure of the proof, or the goal of the proof, is going to be to show, using these 3 axioms that we're assuming, that there is a decisive group that consists of just one person. So it suffices to prove there is a decisive group consisting of just one individual. Okay. All right, so now we're really pretty much ready to get going. The proof is going to be structured as a proof by contradiction, okay? We've done a little bit of that before, but it's really just a process of elimination, right? There's 2 possibilities. There is a decisive group that consists of just one person. That's what we want to argue. Or there is no such group. Okay. So what we're going to do is we're going to argue that that bottom branch can't hold, because if we follow that branch, it leads us to a contradiction. Okay. If we can eliminate that branch, that leaves the upper one, that there is a singleton decisive group. And that means there is a dictator. Right? So the whole proof boils down now to crossing off that bottom branch, to following it ultimately to a contradiction. All right, so let's follow that bottom branch. So let's suppose that there is no decisive group with just one member. Right? That's going to be a supposition that we carry now to the end of the proof. So let's start down this branch. Note that by Pareto, the entire group consisting of all individuals is decisive. Okay, why is that? Consider any preference profile and any x and y. Suppose everyone in this group, which is the entire society, prefers x to y. Well, Pareto tells us then that x has to be socially preferred to y, so the members of this group get their way, so they're decisive. Okay, so that's quite direct. So any decisive group has to have at least one person in it, and we know that society as a whole is a decisive group. Okay. All right, so let me do a Venn diagram sort of here of society as a whole. Okay, so this blob is the set of all individuals. We have noted that this is a decisive group. But there could be a group that's decisive that is smaller than n. Okay, maybe you know, if we leave out a couple people over here, maybe this group here is still decisive. Well, that might not be the smallest decisive group. Maybe if we leave out these three people over here, then, you know, we still have a decisive group. Well, but if we keep looking for smaller and smaller decisive groups, eventually we can't find anything smaller, okay? Eventually we will get to a group that is that's decisive and such that you can't throw anyone else out and still have a decisive group. Okay. So let's suppose that group is G. So let's let G be a group that's decisive. And such that no subgroup of G is decisive. All right, so, you know, if we take anyone out of the group G, then it will no longer be decisive, okay? Well, by supposition, G does not have just one member, right? We're supposing there is no singleton decisive group. We know it has to have at least one member, but it can't have exactly one. That means it has two or more members. Okay. So that means that we can we could partition or divide the group we can divide G into two subgroups. Let's say G1 and G2. Okay. We're just going to, we have this smallest decisive group. We're going to break it up into two subgroups. Okay. Since no subgroup is decisive, that means that G1 is not decisive and G2 is not decisive. Okay, neither of these groups are decisive. All right. Now I'm going to focus on G1 next, but everything I say goes for G2 as well, right? I don't know anything more about G1 than I know about G2. Now, all right, what would it mean for, let me move down here. What would it mean for G1 to be decisive? And I'm going to take the negation of that next, but I just want to see what that would mean. G1 is decisive means that for all x and y, G1 is decisive for x over y, and I can use this decisiveness relation to denote that, right? But we just said it's not the case that G1 is decisive. So it is not the case that for every x and y, G1 is decisive for x over y. All right, so just a little bit of logic here. This means if we take the negation of that, there are two alternatives, and I'm going to give them specific names. Let's just call them A and B, such that it is not the case that G1 is decisive for A over B. Right? I've just taken the negation of this universal statement, and that tells me that, okay, there's two alternatives, A and B, such that G1 is not decisive for A over B. And what does that mean? Well, if G1 were decisive for A over B, I'm going to take the negation of that again, but that would mean that for all profiles, such that everyone in G1, for all profiles, such that everyone in G1 preferred A to B, A would be socially preferred to B. Okay, but we just decided that A and B are alternatives such that G1 is not decisive for A over B. So we have to take the negation of this statement, and this means that there is some profile let's just to single it out, we're going to put a prime on it. So there's a profile P prime such that everyone prefers A to B in that group, but it's not the case that A is socially preferred to B at that profile. Okay, and of course, we have our shorthand for weak social preference, right? So for this profile P prime, everyone in the group G1 prefers A to B, but A is not strictly socially preferred to B. That means that B is weakly socially preferred to A at this profile. Okay, so we're supposing there is no singleton decisive group, and we've then found a smallest decisive group. We've broken it up into two subgroups, G1 and G2. We're focusing on G1 for the moment. Because G1 is not decisive, that means we have alternatives A and B and a profile P prime such that everyone in G1 prefers A to B, but society does not strictly prefer A to B. It weakly prefers B to A. So if we were to write out that profile, the P prime profile, we would have all these people up here. Let's just say that the people in G1 are this first group here. It doesn't have to be like that, but what we're talking about is a situation like this. We have a profile P prime where everyone in G1 prefers A to B. Okay, there's other alternatives in here, presumably. These other guys, I don't know what their rankings are, okay? All I know is that there's a profile P prime where everyone in G1 prefers A to B, but B is weakly socially preferred to A at that profile, okay? All right, so now we're ready to get going. The way I'm structuring the proof is to write down 4 different claims. They're going to be using these axioms, and some of them will be specific to A and B, these alternatives that I picked out. The goal of the claims is to kind of build on each other so that later claims can borrow from earlier claims, and hopefully it's not too intense, but at the end we're going to derive a contradiction. Okay, so claim 1 is that there do not exist distinct alternatives X, Y, and Z such that G2 is decisive for X over Y and G1 is decisive for Y over Z. Okay, so so this is saying, you know, these groups G1 and G2, I know they're not decisive, but they could be decisive for specific pairs of alternatives. But if they are, they can't be connected in this way, okay? And the way I'm going to prove this claim is a proof by contradiction. Notice that we're already in a proof by contradiction. Now we're going to another one within that, sort of a deeper layer, and that's completely fine. You can have nested proofs by contradiction. So what I'm going to do is suppose there were such alternatives. Okay, but then we could choose we can choose a profile as follows. And now I'm going to be choosing some more profiles, and I don't want to get the notation all mixed up. So this profile that I'm choosing now, I want to distinguish it. I've already used a prime, so this one will be a double prime, okay? But I'm going to just choose a profile where the weak orders of the individuals look like so. I'm going to put again, just for illustration, I'll pretend the members of G1 are first, and the members of G2 are next, and then everyone else, I'll put them at the end. Now, in this profile, I'm going to have everyone in G1 is going to prefer Y to Z to X, and if there's other alternatives, just put them below in the ranking. It doesn't matter where we put them. And the people in G2 will prefer Z to X to Y. You can put all the other alternatives below in their ranking. And everyone else, actually, I don't care what their rankings look like, okay? So this profile just has to have preferences over X, Y, and Z for the members of G that look like so, okay? Now, but I'm going to show that this leads to a problem, okay? So notice that, so remember, G1 and G2, so we started with the smallest decisive group, G, and we broke that up into G1 and G2. But that means that G1 and G2 together, and if you know the set notation, that's fine. So G is the union of G1 and G2. Together, they are a decisive group, right? We're assuming that G is the smallest decisive group. In this preference profile, notice that everyone in these two groups, so everyone in G prefers Z to X. So since G is decisive and everyone in G prefers Z to X, that tells us that Z is strictly socially preferred to X at this profile, okay? But we're also supposing that G2 is decisive for X over Y. Notice that everyone in G2 prefers X over Y. So, since G2 is decisive for X over Y, and everyone in G2 prefers X to Y here, we have X socially preferred to Y. And also, we're supposing that G1 is decisive for Y over Z, and in this profile, everyone in G1 prefers Y to Z, right? So since G1 is decisive for Y over Z, that tells us that Y is socially preferred to Z. All right. Now, we're assuming the rationality axiom. So the social preference relation at this profile is a ranking. And what we see is X is above Y in the ranking, Y is above Z. So, if we put those together, that means that X is above Z in the ranking, right? So technically, we're using the rationality axiom here. So by rationality, the social preference is a weak order, and therefore it's transitive. All right. If we hook up those two observations, right? X is above y and y is above z. Then we have x is above z. But wait a minute. We just said that we started by saying, well, G is decisive, so Z must be socially preferred to X. We just concluded, though, that, or we just deduced that the opposite social preference had to hold. Okay? So if there were alternatives that were hooked up like this, then we would actually end up having social preferences going in the opposite direction between X and Z, and that can't happen. Okay, so this is a contradiction. And that means that there can't exist distinct X, Y, and Z for which this chain of decisiveness holds. Okay, so that's claim one. And you can see how we're using the axioms here, and we're using the idea of a social preference function being defined on all preference profiles. I actually I constructed a preference profile here in a particular way, but we're assuming that the social preference function assigns some social preference relation to that profile. And anyway, so that's claim one. So claim two is the following. I'm gonna write it like this. So because it's not the case, remember we had these. We said G1 is not decisive, so there must be two alternatives, A and B, such that G1 is not decisive for A over B. Okay, because of that, we can deduce the following: for all alternatives that are not A and B. All right, so for any third alternative, we can show that G2 is decisive for B over X. Okay. Using, we're going to use claim one as well, but the key here is that G1 is not decisive for A over B, and that lets us actually deduce something about G2. G2 has to be decisive for B over any third alternative. Okay, so that's quite a step up. And so to prove this, we will, let's just consider any third alternative, any X not equal to A and B, and we're going to define a preference profile P, and I've already used a double prime, so this is going to have 3 primes on it, with individual preferences over X, A, and B as follows. All right. So now here, I'm actually not going to pin down the preference profile because I'm going to let some of the preferences here be arbitrary. All right. So what I'm going to do is, as usual, I'll just have everyone in G1 over to the left, everyone in G2 next, and then everyone else over here. All right. Now, first of all, there could be other alternatives. Just put them below in the rankings. I don't care where they are or what they look like. But for X, A, and B, I'm going to specify that everyone in G1 prefers A to B. And now for people in G2, well, here's the thing. For this preference profile, I want the individual preferences between A and B to be the same as in the P prime profile. So let's go back to the P prime profile. Okay, so in the P prime profile, notice that everyone in G1 preferred A to B. And for all those other people, I have no idea what their preference between A and B is, right? So in this profile I'm constructing now, I'm saying everyone in G1 prefers A to B, just like the P prime profile. And then for G2, I don't know what their preferences were in the P prime profile. So I'm just going to put those in parentheses because I don't know really what to put in here. It's just whatever they were in the P prime profile, that's how I want them, okay? All right, so A and B in parentheses means just have them as in the profile P prime. Same for all these other people here. I don't know what their preferences were. So I'm going to have A, B in parentheses here. The point is, that preferences between A and B in P triple prime, this profile here, are the same as they are in P prime. All right, what about X? I haven't put X in here yet. So, so for X, for the people in G1, I want X to be below A, all right? But I don't care if X is better, you know, between A and B, or if this guy is indifferent between B and X, or if X is down here somewhere. I don't care. I want A to be better than X, but between B and X, I don't care. So the way I'm going to represent that is I'm just going to put X here, but I'm going to put brackets around B and X, just meaning, you know, you can have X above B or below B or at the same level. All right. For people in G2, I'm going to put X below A and B. And for all those other people, I don't actually care where X goes. So, you know, it can go in anywhere you want here, okay? So let me just write, so BX here means just arbitrary preference between these alternatives. Okay, so the argument I'm going to give will work no matter how B and X are situated in these rankings. Okay, so fine. Now that I have that, let's now apply our axioms. So since individual preferences since individual preferences between A and B are the same in this profile as they are in P prime, by IIA, the social preference between A and B is the same in both profiles. Well, and in profile P prime, B was weakly preferred to A, so it was socially at least as good as A. So that tells us that B is socially weakly preferred to A for this preference profile. That's just using IIA. Okay. Okay. Now, notice that, let's look at the preferences between A and X in this profile. If you'll notice, for people in G1, A is better than X, and for the people in G2, A is better than X. All right? As we talked about in the previous claim, G1 and G2 together are a decisive group, right? Because they make up this group G. Here's a preference profile where they all prefer A to X, and by the nature of being a decisive group, that tells us that A is socially preferred to X at this preference profile. Okay, so let's just combine these two observations now. So then we have B is weakly socially preferred to A from the previous slide. A is strictly socially preferred to X. All right. Now, if you remember the ranking theorem, so if you have a ranking, then, if you have B at least as good as A and A strictly better than X, then that means B is better than X, right? That's the ranking theorem. Applying that here, we see that, well, B is strictly socially preferred to X. All right. What I want to do, though, remember I need to show that G2 is decisive for B over X, right? That's the whole claim. Now, I haven't shown that yet, okay? I've just shown for that one preference profile, this P triple prime, that B is socially preferred to X. But let's look at the profile again. Okay. So this was P triple prime here. For this particular preference profile, we know B is socially preferred to X. But remember, I didn't specify these preferences between B and X for G1 or these for all these other guys. What I do know is that the people in G2 prefer B to X. All right. Now, if you think about it, we actually have just shown that G2 is decisive for B over X. In other words, using this notation, why is that? Take any preference profile where the people in G2 prefer B to X, okay? I don't we can call it P tilde if you want. P tilde. And here, the people in G2 prefer B to X. I don't know where the other alternatives are. I don't know what anyone else thinks about B and X. But whatever those preferences are, whatever the other people's preferences for B and X are, I can go back to P triple prime and I can put those in these blue bracketed terms here, right? The people in G1 can have any preference between B and X. Same with all these other guys at the end here. Right? So if I have a profile like P tilde, I can just go back to P triple prime, plug in the preferences that those other people have between B and X, and then claim 2 tells me, all right, so B is socially preferred to X. By IIA, that means that the group G2 gets its way, right? Whenever all members of G2 prefer B to X, it doesn't matter what other people think, B is going to be socially preferred to X. So, so in fact, the argument that we've just given here, because this P triple prime profile doesn't rely on, it doesn't pin down these preferences between X and B, we're then able to sort of export that argument to any profile where the people in G2 prefer B to X. All right, that's a long way of saying that we're done. G2 is decisive for B over X. Okay. Now we have a couple more claims. This installment's going long. Arrow's theorem can take a while to do. So we'll just come back to it in the next installment and we'll finish it up. And I'll see you there.